Good afternoon, everyone, and welcome to our panel discussion today entitled Overcoming Well Completion Challenges in the Permian Basin. I am Amr Radwan, CTO and the co-founder of TenEx Technologies, and I have the pleasure of moderating today's discussion. It changed just a little bit of background noise coming from your thing. If you don't mind, can you just mute it? Thank you. So, as we all know, the Permian Basin remains one of the most prolific oil and gas plays in the world. But developing and optimizing completions here is anything but straightforward. Operators, service companies alike face unique geological, operational, and economic challenges. So today we are bringing together industry experts who are on the front line of these challenges, driving innovation and developing solutions in completion and hydraulic fracturing. So our goal is to dive into the key challenges faced in the field, explore the latest advancements that are helping unlock more efficient, cost-effective, and sustainable completions. So here is how our session will flow today. We will start with a brief introduction of our panelists, followed by about 50 minutes discussion covering some of the most pressing issues and the breakthroughs in well completions. Then we will open the floor for the last 15 minutes for a Q&A session where you, our audience, can engage directly with our experts. So to help us navigate this discussion, we have an outstanding panel of industry leaders joining us today. We have Dave Cramer from ConocoPhillips, Amit Singh from Chevron, and Qin Ji from Oxy. So before we start our discussion, can you guys, Dave, Amit, and Qin, just give a quick introduction about yourself to our audience today, and just a quick 1 minute, overview about your backgrounds. We will start with you, Qin.
Hi, everyone. Can you hear me clearly?
Yes.
My name is Qin Ji. I'm the completion engineer for Oxy. Right now, I work for the Permian Basin, and my current work is involved a lot of fracture modeling, science projects, designing, optimize the completion design for the Permian. Yeah, I have 7 years of industry background. The other two are the experts. I'm here to learn too. Yeah.
Thanks, Qin. Amit?
Thanks, Amar. Hello, everyone. Amit Singh. I work as a stimulation advisor in Chevron. Been in industry for almost now 25 years, 12 years with Chevron. My most focus areas are heavily kind of related to the completion and the fracturing optimization for our unconventional assets in Chevron. So hopefully we will talk about in terms of like how some of those things we have progressed in the prior years and where we are heading towards. So looking forward to more conversation. Thank you.
Thanks, Amit. Dave? Now we can't hear you, Dave. Now we do.
Can you hear me?
Yes, we do.
Okay. Yes, I am Senior Engineering Fellow with ConocoPhillips. Got 48 years of industry experience. 17 to 18 years of those have been with ConocoPhillips here. I've got a 30-year history with pumping service companies prior to that, mostly with BJ Services. I was their region tech manager in the Rocky Mountains for 22 years. So hydraulic fracturing, well stimulation, pressure analysis, those have been my specialties during that time period.
Thanks, Dave. Thank you guys for all your introductions. Okay, so with that, let's get into it. So let's dive into our discussions. The first question I have today will go to Amit. So the rock formations in the Permians are very different from one place to another. So do you adjust your completion designs based on these variables? And if so, how do you approach that?
You're right. Like so, I would say when we talk about the rock variability or the heterogeneity, we have to talk about the scale at which we are considering those variability. So we definitely know, like, hey, the rock properties across the different basins within USA itself is there is significant variability. Even if we come to any specific basin for like Permian, within Permian, like Midland Basin and the Delaware Basin have the variability within each of those Delaware or Midland different development areas, different formations have the rock variability. So the simple answer is yes. We do have different completion designs for the different development area, different formations. There are a lot of information that goes in when we select and we talk about like, hey, which design we want for which well or which bench or which development area, what we call the playbook designs. So we have playbook design for the different areas, and the kind of information that feeds into to come up with the playbook design is learning from the industry. Like industry has done a lot of different design options that we can take a learn from, like, okay, which of them have worked, which of them have not worked. On top of that, the technical learnings and the technical information, the first physics part of it, in terms of if we have a good understanding for the rock type, like what kind of rock it is, what the petrophysical geomechanical properties is, then how do we decide on their part, and definitely the modeling and the simulation that goes in that part. As we go through the different designs, the continuous learning goes in, and we change the design with time as well perspective. One thing I want to highlight also is, like, when we talk about the designs to respond for the rock properties, we generally do not change the designs from one well to another well if they're in the same bench, in the same pad, or we do not design or we do not change any design from one stage to another stage unless until there is any new information that is available to us that convince us, like, yes, we do need to change the design responding to those specific ones. So that's in a nutshell, I would say. Like, the design parameters, the design changes as per the rock. Yeah, we all change it and we optimize it for that given rock properties. Yeah.
All right, thanks, Amit. I appreciate your thoughtful answer on this. So, Dave, I have a question for you, and I know a lot of the papers and the researches and everything that you have done. So that question goes to one of the most talks about one of the biggest challenge that we see. So how do you, which is basically frag-driven interference, or for short FDI. So how can we reduce frag-driven interactions in general in wells, both that are regularly spaced and tightly spaced? How do you usually approach that?
Well, in the Permian, we've done a lot of experimenting with all the different techniques, open parent, refracturing, using materials in the fracturing flow to try to prevent direction in depleted areas. But
Dave, Dave,
yes,
I feel your speaker has a problem. Are you using something wireless or something?
I am not. I'm just using the computer speaker. Can you?
Now it is great. Now it is great. Yeah.
Yeah, could be
Sorry
an
for
internet
yeah.
problem, maybe. Anyway, going back to that question, one thing that we have that's been effective for us in the Delaware Basin and is to shorten up the frac stages. So from our typical 200-foot frac stage, 8 clusters per stage, 25-foot cluster spacing. We just cut that in half. So we're pumping the same volume per cluster, but at a higher injection rate. We've seen that we get better uniformity based on both fiber optic and perforation erosion analysis. I think we get more height, and we have less. We have a more uniform, treatment in both directions. So it's not eliminating frac hits or fracture-driven interactions, but we see much less damage to the producing parent well, and we're getting better production from the child well. So that's what we've seen in the Delaware Basin. We've seen some really encouraging results in the Eagle Ford that we may be applying to the Delaware Basin, and that's the use of a polylactic acid fine mesh material that we add to 100 mesh sand. After we've pumped a bit of a quantity of 100 mesh sand, this mixture gets very viscous, and it hasn't eliminated fracture-driven interactions, but we've seen a significant improvement with these interactions in the parent well. We've actually seen usually stimulate, increases in production, which in Eagle Ford, the norm had been decreases and sometimes total well loss. And it looks like better performance in the child well. So that's something, it's a technology borrowed actually from other operators that was brought to our attention by the vendor. And again, we're seeing the hits, but the consequences of them are much less. And that's recently decided that we're going to do this on all of our treatments in Eagle Ford. So, we're testing in Bakken and the Permian. It's just a matter of time before we'll, look at that option.
Oh, thanks, David. So when you say you have been doing this in the Delaware, that talks about all benches, Wolfcamp B, C, 8, like you're seeing this in, despite the formation, the same design works with the
Yeah, the dominant work historically has been with Concho Resources. So we acquired Concho 3+ years ago, retained just about everybody from Concho. So we've got a deep history, but they were heavy Wolfcamp players, right? In particular, Wolfcamp A. So most of our stuff has been like wine rack, fracturing techniques in the Wolfcamp sand and the Wolfcamp shale. We basically pump 200 to 200 and to 2,500 pounds per linear foot. So it's on a linear foot basis, just like everything. And 2,000 to 2,500 gallons of slick water. And it's just slick water. We do not try to build viscosity. All we care about is pipe friction there. So it's very uniform, very factory-like. Now we're starting to develop more in the sea. We're also acquiring and building an extensive data set that we're applying machine learning methods to. We're more advanced at this in Eagle Ford, frankly, than in the Permian, but I think we will see area changes over time. And as we get into the Bone Springs, that's been very lightly developed by ConocoPhillips, but it's a more permeable sand. So you're going to, even though we've started out with the same factory mode, you're going to see wider cluster spacing, probably wider distances between wells, and different pounds per foot. But ultimately, the goal is to get very factory-like. We're solidly behind that. Although I think we'll evolve to do like Chevron does, tweaks in different areas. The big thing is how are we next to depletion, and there are more changes driven off of that in technique than there are reservoir quality variation.
Oh, thanks, Dave. I appreciate that. So, Chen, changing topics a little bit and talk about the water we use for fracking. So, do you think operators can fully rely on produced water for frac operations, like I mean 100%, or do you still see fresh water in the need for fresh water in some cases?
It really depends area by area. In Oxy, we are relying on produced water for frac operations. However, there are challenges such as the availability of the water resource, regulatory constraints, and the cost of the recycling process. In Delaware Basin, significant progress has been made in sourcing and recycling water, demonstrating the feasibility of relying on produced water for frac operations. However, the produced water quality varies, right? The salinity, the total dissolvable solids TDS can vary. The compatibility of the produced fluid with our additives needs to be tested thoroughly before we're using it. Yeah. So sometimes we can use 100% produced water, but sometimes we need to add fresh water to have a mix to blend. Yeah. We are trying.
And you think that basically can become a standard across the basin now?
Sorry, say that again.
And do you think this could become like a standard through the whole basin now, or just limited to the Delaware, or so? Like, is there a big difference between the Midland and the Delaware when it comes to this, or the different formations that we see there, or think that's, we could see this trend become the norm across the board?
Actually, I am not 100% for the Midland, but for Texas and New Mexico, the Delaware Basin, we're almost there. Yeah.
Right, thanks, Chen. So, Amit, with so we see most operators use 100 mesh 4070. I mean, specifically local sand nowadays in their completions. So, are you doing any more probe and testing, or have you guys found an optimal type that works across most wells right now, and has become like a factory design for you?
So for the Proppant in Permian, I would say definitely the 100 mesh is our preferred Proppant in the sense like from the playbook side, from the factory side, 100 mesh sand, the local regional sand is our go-to sand type. Now, so I would say we are not exploring anything specific on that majority or the primary Proppant material. There are definitely other technology options, other component of the different proppant material, the sizes, the distribution, those are being considered as an add-on or a certain percentage of the overall job. But the primary proppant material is 100 mesh local sand for the Permian. Now there are few other areas like we have Chevron also has operation in Rockies. So depending upon the rock requirement, depending upon the conductivity requirement, we do select some other prop and mesh size as well. But those variations are mostly on the mesh sizing, not on the composition. Like it's still a natural sand part of it.
So even that goes to all formations as well, like all benches, including like bonus spring, that you see the 100 mesh would be the dominant across the board.
Yeah, in Permian, we are very comfortable with 100 mesh sand across all benches. And the reason for it is like when we talk about Bone Springs versus Wolf Camp or things like that, like, yes, it's a relatively higher permeability, but still it's very low permeability. From what we have considered, what we have reviewed and analyzed, we are very comfortable with 100 mesh sand even on the Bone Springs.
Thanks, Amit. Going back to you, Dave, with a question. So we talked about water, proppant, now chemicals. So when it comes to the chemical design, do you focus on simplicity, simplifying it, or any new additives that you guys are experimenting with? We see, for example, some operators stopped completely, or a lot of operators stopped using surfactant as an additive. Is there anything else that you guys are trying to experiment with here, or we basically focus on the simplification approach?
So we do have a pilot project where we're taking another look at surfactants, so-called nano surfactants, and the ability for these surfactants to go in and at least get us some incremental oil. We're evaluating the results right now. However, for the past 10 years, ConocoPhillips has been very simple. Back when I came on board, we were just starting the Eagleford play. We still had vertical pilot wells for testing, but we eliminated clay stabilizer. It was a great feel-good thing. You had to put clay stabilizer in there, even though they were absolutely not needed. So that was eliminated. About 3 years later, surfactants, and these surfactants are really to prevent bulk emulsions, the types that were being used. They were eliminated. All that was left, and we, for a long time, we pumped high quality cross-link gels. That's been the most recent thing. ConocoPhillips was one of the last to depart from that trend. That being said, we got some awesome results with cross-link gel fluids. But it's as simple as possible. Pump enough friction reducer with salty water to get low pipe friction, maybe not the lowest pipe friction, but there's a balance between material cost and horsepower cost. And as part of the water treatment, take bacteria very seriously. So, I mean, it's a surface bacteria kill. We knock iron out. We extensively treat for bacteria and, try to use as much recycled water as we possibly can. And that's about it. We'll see how the surfactant test comes along. Maybe we'll bring stuff back in. Like I said, in Eagleford, we're now looking at using it's not a surfactant or a traditional chemical, but an additive to help improve the imbalance towards depletion. There still could be some room for microproppants, as you and I've talked about, although it's tough to get some of these things that we'd like to test to tweak the results on the program. People are really comfortable with the bare bones approach here.
You mentioned if our salty water and you are already pre-treating the water with, for bacteria using biocide, iron control and all of that. Are you still adding, or do you add a scale inhibitor to your frac design?
So you mean scale inhibitor? Is that what we're
Yes.
talking about?
Yes.
In certain areas, we do. It's not common. As far as I'm aware, anywhere in ConocoPhillips. Now, I haven't recently talked with the Bakken guys. We used to have a program there where we pumped it on every well. But in the Permian, that is uncommon to pump scale inhibitor. So, no, not. Is that a mistake in some areas? Are we missing out on an opportunity to delay scale formation? Quite possibly. But simplicity is won over. Now, maybe as we get more information with our, data and apply machine learning and look at those results, maybe we'll start to, reintroduce that in certain areas.
Thanks, Dave. So going back to you again, Chen. So in long laterals, do you see challenges with proppant transport? And if so, how do you solve them?
Thanks for the question. Yes, nowadays, more and more longer lateral wells were drilled and completed. We in Oxy use advanced fluid dynamics modeling to simulate the behavior of proppant within the fracture network. This helps us understand how proppant moves and settles in the long lateral sessions, allowing us to optimize our pumping schedules and fluid formations. We use tailored fluid systems that are specialized, designed for the long lateral sessions. This will help us maintaining the proppant suspension and transport. These fluid systems often include viscosifiers, friction reducers, and other additives, which can enhance the proppant transport properties. Yeah.
Are you guys usually using 100 mesh also across the board now, or you are seeing that varies? That challenge varies based on the proppant type.
We are mainly using the 100 mesh sand. Yes.
All right. Any experimentation with even finer materials, or 100 mesh is what you guys are settled on?
Finer materials like higher mesh and 200 mesh.
Yeah.
We are testing the blend. Still evaluating.
Thanks, Chen. Amit, since we are talking different approaches right now on for different wells also, so when it's come to the perforation design across different wells and within the same well, do you have you guys settled on a standard approach for certain areas, or there is still some ongoing experimentation there happening with the perfect design?
For the yeah, okay. Let me walk through a little bit on this one, because, and I'm sure like Dave and Qin Ji has a lot more to share on the perforation design as well. Like Dave has been working on these things for many years. So when we talk about the design or approach, I would say there is very common solutions on that approach in terms of the goal is to achieve that uniform distribution, as you mentioned, and the mechanisms to achieve is having good reliable perforation friction, limited entry perforation friction design, and a good understanding of how the proppant dynamics, how the overall fluid and the proppant slurry dynamics taking place within the wellbore, and I will say add on into across the different individual clusters part of it. So the approach is to use these information to come up with a recommended design or come up with the best design that gives us the uniform slurry distribution. Now, I would say definitely add on there is extensive work has been done from the laboratory basis, modeling the CFD modeling, computational fluid dynamics, and within Chevron, we have some internal tool that incorporates these different mechanisms for the perforation friction, limited entry, as well as the neural network model that can represent or kind of like a simplistic version of the learnings of the proppant dynamics that is coming from the CFD modeling. So those learnings, those informations are incorporated within the tool that we use to come up with that optimum perforation design. So those are the approach, I would say. Now, when we take those solutions, those tools, those learnings, then the perforation design is optimized in each and every well, as well as in the different stages, depending upon what the expected pump rate that we can achieve, as well as how many clusters we want to treat, what's the cluster spacing is, what the rock properties are in terms of understanding the stress shadow component of it. So a lot more physics, a lot more design variables that goes in that tool, in that physics part of is to come up with the design solution. So the solution will look different in different wells, but the approach, the goal, the tools, there are a lot more commonalities, and I would say the learnings, the base physics is still those things that are incorporated there. Yeah.
Okay, I appreciate that, Amit. Dave, I know, as Amit mentioned, you have done a lot of work on the perforations. So if you want to add just your 2 cents here, would really appreciate that.
So we've done a lot of work in this area before my time at ConocoPhillips.
Hey Dave, your audio is again breaking kind of or very loose.
Okay.
Okay, it's
How
better
about
now.
now?
Yeah. Yes.
Okay. Great. Thanks, Amit. So, yeah, we've done a lot of research. That research is kind of tailing down, although I will note we're involved in different consortiums. The most notable peer consortium that's trying to do special tests, looking at data to come up with improved limited entry modules. So that ultimately could allow us to do a little bit more design work, but we're really down at this point in time to rules of thumb. So in Permian, and really it's not that much different in Eagle Ford or Bakken or Montney, our other major plays. We're targeting about somewhere between 13 and 1500 psi initial perforation friction. And you're going to see variation just based on hole diameter variations from perforator vendor to vendor or gun type to gun type, although we do a lot of work with our vendors to make sure that we have a charge that's reliable and consistent on the surface. And we vet these vendors. So there's a lot still ongoing work whenever we're trying to, introduce a new vendor approach. We are believers in oriented perforating. So typically that's 12 o'clock position high side, although I really don't think at this time that the inclination matters that much as long as it's the same inclination. And also having, minimum of 3 perforations. So the three to four perforations per cluster. And again, we got to balance that with the number of clusters and, trying to achieve this initial pressure drop, which is going to go down as we erode the perforations. But, the more perforations, jet perforations are jet perforations. Everyone is different. And with all the work that you do with the vendors, there's a variation that's in part dependent on the gun clearance, the distance between the perforating gun and the interior of the casing, but just there's natural variation. And so the more perforations you have, the more these natural variations play out, balance out. Also, if you're at a consistent gun phasing, there's going to be less variation. So that's one plus with having more than 1 or 2 perforations. The other thing is that it seems that reduces the inertial effect, which is the tendency of some proppant not to turn the corner with the fluid and go into the perforations uniformly, but miss perforations and then work its way down towards the toe of the well. That is largely a self-correcting effect, especially with 100 mesh sand. If you have 3+ perforations, there's a real tendency for that first perforation to have more bypass than the others. You'll see it to be the least eroded perforation, but it's really standard. We do the same thing in Midland Basin as Delaware Basin, and really in Eagle Ford and Bakken. And boy, we're a very standard company when it comes to that. Now, if we knew a case where we had more stress variations amongst that stage, we would be tempted to run to a higher delta P, reducing perf diameter, taking that out. We don't have any real reason to believe that in any area, but in doing that, you're also accelerating erosion too. So you're kind of working against yourself as well as building up, cost ultimately by having to pump more hydraulic horsepower. So, we've been experimenting for decades now, and we're not huge believers in extremely high differential limited entry perforating, although that would be a go-to thing if you thought you had a lot of stress variation due to stress shadowing or just a lot of rock property changes.
Thanks, David. I appreciate you adding your insights into this. I know we can have just a complete panel just discussing perfect designs. Maybe we need days actually to discuss that. Thank you guys for walking us through your overview about how we are approaching it nowadays. So, Chen, I have a question for you. I know you do a lot of modeling, and we have a lot of students here on the call today. So I would like just to simply tell them what role does modeling play in understanding and predicting fracture geometry overall?
All models are wrong. Some are helpful, right? Fracture modeling, we do that a lot in Oxy to understand. I think the most valuable point for the fracture modeling is the sensitivity analysis. First, we need to create an accurate, or I cannot use the word accurate because I don't know how accurate it is. Even with the science diagnostics, it just helped me understand how my fracture looks like, right? But we need to have a good understanding of our base model. Our base fracture model needs to be somewhat make sense. It either match the hydraulic fracture, not hydraulic, the oil fracture height of the geochemical oil printing, the vertical oil printing, the height, or match some of the like the microseismic, the cloud. There are different diagnostic tools that can help us understand our fracture modeling. And after we get a good understanding of the fracture modeling, we can use that, leverage that to test the different completion designs and test the different depletion scenarios of the parent. I think that is how we best use the fracture model. Yeah.
So you said you do a lot of modeling at Oxy. So just give our audience here just an idea about how often this happens. Like, for example, do you model for every stage? You model for every well? You model for every area? And how often that modeling goes back to your operations and that plays a role in changing your design or approach overall?
That is a very good question. I have last year I have 10 projects just for modeling. We are trying to do the fracture modeling for all the appraisal wells, since this is the wells or the benches that we want to understand more and tweak the completion design more. And for the appraisal benches, appraisal wells, it's also, we put a lot of science on it to get the best calibrate model and history matching. And then run different scenarios for our next ESU, how many wells we should put in one session, how far away we should put this child well to the parent, what is the optimized completion design, should we make it bigger or smaller? Yeah, so I do a lot of modeling, 10 projects per year.
Oh, wow, that's definitely a lot of modeling. Thanks, Chan. So, Amit, so we know over time, different frac operations ideas start to kick in. Simul-frack has been around for some time right now. I know people do even G-frack and probably going farther. So, can you just walk us through why people are doing it and what would the key lessons learned from the semi-frac operations as of now?
So the key goal is being efficient in the sense like, hey, if we have a certain volume that we want to inject in a pad or in a multiple wells in that pad at the same time that we are completing, then how quickly we can execute it. Yeah. So that's the surface goal. Only given condition with that is how do we still keep our subsurface design or our downhole design, our design goals, very similar part of it. So the big picture when we move from the single well or the zipper frac to simul frac where we are pumping two wells at the same time, and now triple fracture where we are pumping three wells at the same time. The key objective is become more efficient, and when we become more efficient it helps us on the cost reduction, as well as getting more number of wells completed in a given time window, the number of frac crew that we need, etc., etc. So many other benefit that comes in. So when we transitioned from the zipper to Simul-frack, and I'm happy to share that, like, for Chevron, the Simul-frack is a default design. Like, we always start with, like, hey, uh, Simul-frack is gonna go. We are moving toward the target of making triple frac as a default. Like, hey, why? So the conversation has to be, why can't we do the triple frac? What are the barriers are there? So those are the lessons learned component that will come in their part of, yeah. So the learnings when we become more efficient, the learnings that comes with it is you have to have other operations as well to meet that efficiency improvement uh, benefit part of it. So for an example, if we are becoming more efficient and we are pumping a job that would have taken 30 days to finish in a pad, if we are finishing in 24 days, then you can imagine that the amount of water requirement as well as amount the sand requirement, the equipment readiness, the equipment repairing part of it, all of those are gonna get accelerated. The pad footprint that needs the number of pumps need to be properly accounted. So a lot of detailed operational planning that has to go through to account for everything that comes with that efficiency improvement. Once we have done that, then the job goes very smooth, everything runs as smooth. But to be able to achieve that efficiency improvement, we do need lot of other planning to be done, lot of other drivers and the impact to be properly considered. And once we go through those, once we have gone through those, we are very it's not a lessons learned part of it. It is just like, hey, you need to have those things lined up, otherwise you won't be able to achieve those efficiency improvement, yeah.
Thanks, Amit. And you think like all service providers, small and big, are equipped to do semi-frac right now, or there's still some that are a little bit behind the curve?
um I won't be able to comment on, like, hey, what the service provider can do or cannot do. I think it's more about, if an operator A is exploring the option for doing it, then they need to have the conversation uh, with their preferred pumping company to go through it. It's not only about the uh, pumping companies not able to do it. It's a lot of other thing goes in terms of how many crews that they have to support, what people and what equipments are available, as well as contractually, are you truly expecting that benefit or not. So a lot of other drivers will come in terms of making sure that you can achieve those benefits or not. And as I mentioned, it's not just the uh, pumping companies or the operator part of it. It is more about the benefit of those efficiency and the planning that takes or the requirement that takes in, or the other things that we have to consider, kind of like, if we have to deliver that increased acceleration amount of water, then you need more water pits, you need more water sourcing coming in. So those are the things that goes in. And I don't think it's a function of a small versus big operator or things like that. It is more about, like, hey, have you reviewed the full life cycle and all those components or not, and then come up with what the overall benefit is, and how do you plan for it, yeah.
Thanks, Amit. Uh, David, between tracer, microseismic, fiber optics, and other diagnostic tools, do you have now a preferred, overall, when you basically balance cost versus efficiency versus accuracy, what diagnostic tool give you the best insights into stimulation effectiveness overall, or across the board, or it basically case by case basis for you?
Case by case basis. And I will say this, pressure is the number one go-to diagnostic that's really probably has the greatest potential of providing insight. It's the most economical. And we've been using it for years. So what I mean by that is treating pressure. So, for instance, one of our engineers, data scientists, has come up with a cluster screen-out index. And so being very aware from pressure responses, whether you're maintaining injection or not, usually pressure analysis can give that to you without any need to do more sophisticated diagnostics. And we do know that cluster screenouts lead to poor performance. That has been established. And as well as frac plug integrity, right? That is something that we saw a significant issue with dissolvable frac plugs, which has led us away in most areas from using that basic pressure analysis, but doing it on a routine basis, continually to where we and having that data to where we can go and look back, and we have simple tools to screen out index tools or frac plug failure tools based on pressure. So there's that, of course, offset well when we're getting frac hits. We routinely, instrument our offset wells with transducers, and we're watching that during the treatment. Not that we're necessarily at the point where although hopefully one of these days we might be, where we're making real-time changes, but it's very instructive. And in terms of identifying and very economically these fracture-driven interactions. We've done a lot of perforation imaging, which has helped us, and I think maybe is sometimes more meaningful than even fiber optic in telling us how uniformly we're distributing proppant. And that's helped us optimize in perforating strategies, the need for orientation, that type of thing. It led us to going to 100-foot cluster, 100-foot stage lengths in where we're adjacent to parent wells. That type of analysis. Of course, it's quite a bit more expensive. We're seeing less use of that as we think we've really learned 90% of what we wanted to learn. We occasionally go to fiber optic and treatment wells, but only in special cases. Like we have a well where we have 100% sleeves with intelligent dart system, and so that's equipped with fiber optic. We're going to do perforation erosion analysis. We have internal and external bottom hole gauges because we really want to know how effective this sleeve technology is, right? So we put a lot of time and money into that. We're doing one of those projects this year for the whole company. So I mean, it's anyway, I hope that helps. But I mean, it's pressure. That's the number one diagnostic in various forms.
Just a question that I just came to my mind right now. So let's just say you are doing 100, 100 frac year. How often do you run diagnostic on them?
Okay, say that again.
If you are doing 100 frac year, 100 bad year, how often? Yeah, how often you run diagnostic on them?
Okay, so we were doing well. It depends. It depends on where we're at. Montney, we're developing, but it's still in a lot of ways an appraisal. We've got this vast amount of acreage. And so there's no going in between, parent wells to put child wells. It's all pretty much new stuff, although we are bumping pad against pad now finally. But we, do a lot of perforation erosional analysis there. Maybe every other pad will have we'll run fiber in the treatment well. And so there's more, that was the way it was in the Permian 2-3 years ago. And we're really trying to understand limited entry optimization, cluster space, and that includes cluster spacing, stage length, all of that stuff. Now we think we figured a lot of things out. So that in that 100 wells, maybe it's down to at most 10 wells, whereas in Montney it would be 30 wells. And
see.
maybe 10 wells is stretching it. Maybe it's only 5 wells now. I don't know. With the advanced diagnostics that are going to cost you $250,000 or greater per application.
Understood. Um, so, Etienne, when we talk about modeling and the digital technologies between AI, machine learning, real-time data, um, any of these technologies in particular you think will shape the future of completions, or it has to be hybrid between them?
I feel all of them can be very useful. Digital technologies such as Internet of Things, cloud computing, and advanced analytics will help us shape the future of completions. These innovations will drive automation, improve operational efficiency, and enable data-driven decision making. I do wish that we can make more real-time decisions or changes during fracking, right? With more horizontal wells, logs, and the data we gather during drilling, we can probably engineer more of our fracturing work, fracturing designs, and optimize the completion design along the lateral in real time. Yeah, as what David mentioned previously, monitoring the parent-child well frac DIs. If we have all the parent well equipped with the gauges, have the child well looking at monitoring the between pad, even between the stage FDIs, that will help us understand how we frac our wells better, right?
Oh, got it. So I have actually, I keep receiving from Ahmed a long list of questions. So we'll just take two more, ask you guys a couple more questions, and then we can probably open it for Q&A so we can cover as much as we can. Um, and this question, actually, I would like to get, 30 seconds, 1 minute answer from each one of you guys on it. When it comes to the cost savings measures, a lot of things have been implemented as we have been discussing through this last few minutes about, using local sand, simplifying the operations, and all of that. Simul-frack, like all of them was mostly trying to achieve the goal of save more but and improve the efficiency. So the question is, what cost saving measures have been most effective for you? And is there anything else we can do to save more, or basically or saved as much as we could, practically save as of now? Amit, we could start with you if you don't mind.
So quick answer, I would be like, so again, efficiency perspective, simul-frack, triple frack has been very, very effective for us in that cost reduction and getting that efficiency. The other one is the fluid to proppant ratios, I would say, in terms of like, hey, what is more priority and how do we optimize that design? So there are good progress being made, incorporating many other things. So the moment we have to pump less, then the cost definitely goes down. So those are the top two, I would say, has been the most effective.
And any more you think we could save, or we have saved as much as we could now?
I have my general answer is like innovation never stops. So I will not say we have reached to the limit. It's just, yeah.
Thanks, Amit. Dave?
So yeah, in Permian in particular, simul-frack's been a big thing. So 3 of our 4 frack crews that or spreads that we use are now doing simul-frack. Interestingly, in the Eagle Ford, they went from 25% to 0. So Permian sees an economic advantage, and clearly you're able to do more feet per day. There's no question, lateral feet in both areas. But it was not economic in Eagle Ford. They don't do it anymore. So just it's deeper, higher pressure. That probably has something to do with it compared to the Permian basins. Mine cut sand is something that they're looking at now. We've done wet sand. Mine cut sand is where they don't go through the extra step of running the sand through a hydrosizer to split nominal 100 mesh versus nominal 40/70 mesh sand. It's all what you get. That saves money. I'm a little concerned that maybe having a bigger, more larger particles is going to lead to more cluster screen outs. It certainly has done that in Eagleford. Haven't heard that reported yet in Permian. Let's see. Reducing water. That's been more of a thing in, so in other words, the way they look at it, increasing your proppant concentration. It's just pumping the same amount of proppant with less water. What can we get away with? Again, more of a thing that we've applied in other areas like Montney. We had a dramatic reduction in water, increase in proppant concentration. And, friction reducer costs money, even if that's the only thing that we've done. We also went from going from trying to get some viscosity to just worrying about pipe friction. Friction reducer costs as well as water costs came way down, an enormous impact. Now, what did we give up in production by by sacrificing hydraulic fracturing area? That's what we need to evaluate now. But continuous fracturing, something more done in Eagleford as a routine, just being introduced in Permian, where we never shut down. Now, you better have the state-of-the-art flexible pipe type of systems in place, both behind your frac pumps and at the wellhead, to be able to go from one well to another without ever shutting down. That saves a little bit of time. And, time is money out there. And so that's something. But we're to those kind of tweaks now, Certainly, that's not as big a deal as Simul-frack. Backing way off on water, that is probably the most impactful thing. But of course, at some point where you back off too much.
Understood. Chen, do you want to add anything to this list, or you think Amit and Dave covered most of it?
I think the industry are doing very similar thing. In Oxy, also Simul-frack, and change the proppant fluid ratio, try the wet dry sand. We're still evaluating that, and then optimize the additives. We also are doing the continuous fracturing, as what David mentioned. Also, extended long lateral, drill longer wells can also help reduce the cost. One more thing I want to mention is maybe some people will say cut the science will save you millions of dollars. I disagree with that. With science and diagnostic tools, it allows us to evaluate the completion design during or right after the fracking. We no longer need to wait for 6 months of production to run RTA. I think with the diagnostic tools, the science, we can apply the learnings immediately to the next ESU. So I do think the science is still necessary. It's how we optimize the completion design. Thanks.
Thank you, guys. So one last quick question for the three of you again. It's actually a request, not a question, more than a question. So I would like each one of you to give an advice to our awesome young engineers that we have them here today on the call of how to succeed in their careers. Amit, we'll start with you.
Since we are talking about Permian, I will use the Permian example to advise something. And that is in Permian, we have seen like, hey, 10, 15 years, the industry has evolved. Industry has evolved with many new things, many new ideas that we thought like are not possible, but we attempted, we hit some roadblock, but we kept on doing and we are improving. Yeah. The same thing I would say. Be open to new ideas. Be innovative. Think beyond something that you are around every day. And as long as you keep that positiveness and improvement, don't worry about marginal or big or major. Every improvement is improvement. So continue looking for that and open to new ideas, and things will get better. No matter which part of life and which part of career you are in. So.
Thanks, Amit. Dave.
Well, yes. So So I got two things. Find a niche. Something that somebody else hasn't done, or is, there's been a little bit of work at that. Find and pour yourself into that. And sometimes you'll hit pay dirt.
Dave,
One of my niches early on was this
Dave, I
Bakken
believe
shale
the
formation.
voice is not clear.
Can you hear me now?
Oh yes,
Yes.
Mr. Barrett.
Okay. Anyway, find a niche. That was the number one. Early in my career, I was a treating engineer, and we were fracturing the Bakken Shale, which was a bailout zone when the Red River Formation in the Williston Basin didn't pan out. And I'm going, what the hell, fracturing a shale? And they really thought the reservoir was in the organic shale back then. So I found every Bakken well. It was all vertical wells back then, and learned a lot and wrote papers, had seminars, and all of a sudden it became a big deal. Limited entry is another thing. That was a niche, something that had been done but had been lightly covered technically. So that's one thing. Find a niche. The other thing is do what the other guy isn't doing. In other words, work harder. I remember when I was a young management trainee with the Western Company, and oh man, they're sending us out of district. Hey, I want to go. I went on as many jobs, did as many things, operated as many pieces of equipment, got into and that's how I branched into the technology. So do what the other guy isn't doing. In other words, work harder than the other guy is doing. Focused working harder, but those are the two big things. We've got kind of gotten soft as a society over the years, so you can make a big impression by working harder. Somebody's going to notice. Somebody important.
Thanks, Dave. Chen.
Yes, I will say there are two things I'll mention today. One is seek mentorship. I feel like I'm super lucky through my career so far. All my mentors are all my role models. I've learned so much from them. I constantly talk to them. So seek mentorship can help you a lot. The second thing will be build a strong network. Go to the social events, talk to people. You never know who will give you some new ideas, who will help you in the future. The third thing will be brave. Always challenge yourself and step out of your comfort zone. Put yourself on the place that you have to try. You will grow. Thank you.
Thank you, Chen. Thanks, Dave. Thanks, Amit. Actually, I've been taking notes. Great advices for all of us, actually, even for those who have been around for so long, to remind ourselves of how these things are important for every day. Now we have about 12 minutes left, and we have some questions here, really actually good questions. First question I have is the increase in perf density help to reduce the treatment pressure? And how about perf phasing, like 60-degree versus 120-degree? Who would like to take this question?
I can, I guess, address that. So again, and I noted this in my previous answer. I think there's solid evidence that perforating in a line works well. Now that line could be 90, 270 or some other, but with existing equipment, sometimes that can be really hard to achieve. Why make life complicated? Just try to go in one direction. Now, I don't think it matters that much whether it's up high, sideways, 90 degrees, 120, but having multiple phase perforations, now that we're down to 2 to 4 perforations per cluster, with as many clusters we're pumping, and to get that minimum limited entry pressure that we'd like to get, 12 to 1500 psi, you know, that kind of constrains you a lot. But yeah, those are more important than maybe the slight difference, and really hard to peel out by the information I have in frac efficiency going high, low, sideways. Just go in the same direction. And make sure you have limited entry. I mean, going in with, oh man, I want to lower my treating pressure. I'm going to put more perforations in there. Now I'm down to 500 psi perforation friction. That ain't enough. We know that.
Great answer, Dave. Second question I have, what are the top three key factors considered in one completion plan in the Permian? Chen, do you want to take that?
For the planning, you're saying?
Yes, for the completion plan in general. So I assume to talk about the modeling and like if you plan a new frac job, what are the factors that you need to consider?
Not like the cluster spacing, well spacing, and the stage spacing.
Yeah. So yeah, that's. I mean, yeah. Some of these questions are coming from students, so they want to basically get an idea about the simple answer.
So to plan a frac job, you need to understand first: is there a parent well nearby? Is it a depleted well? And second, you want to understand: is it an infill well or an edge well, right? If it is an infill well, then you can follow your regular flow chart or the playbook that Amit mentioned previously. If it is an edge well, maybe we can make the completion design slightly bigger. And another thing, you can, is there like a risk in a different landing? Is there a landing you want to dodge? Is there higher risk on water risk on the upper that you want to have a smaller height? Is there any, you can actually change your cluster spacing or change your job size to make your fracture smaller to dodge this shallower risk. Yeah. So I'll say the parent depletion, the edge well situation, and other bench situation risk.
Thanks, Chen.
Yeah, so maybe I can add something. And yeah, you are right. Like when we talk about the three key factors, like you can go at many different scale. Like what kind of factors we are talking about? I will maybe something I will just chime in here for us to consider, because like, hey, if we are talking truly about like, hey, how do we plan completion or the frac? How do we come up with that answer? Like, why this design in this well or this area, whether it's Permian or anything? Then, and if we have to think about three big picture or the three big parameters, I would say we need to understand what the rock needs are, what the porosity, permeability, zone thickness, stress conditions. So, what is the rock need? The second is what kind of other information do we have available from the other operators, from the physics perspective, from the modeling perspective, from the surveillance or the diagnostic perspective. And the third that is most critical is what is the economics gonna tell us? Because yeah, we can design the best design that is possible for the maximum production, but if it is not economically attractive, then it's not the good design. So understanding the rock need, understanding the information we have, and understanding that it has to be economic, then those things helps us to come up with like, hey, what design, what is specific parameters and things like that will you will consider those, and you will optimize or you will come up with that design part of it. Yeah. So again, the challenge with is like what level of factors we are talking about is very open. So yeah.
Probably we need to schedule another panel specifically about that. Another question I have here: how can water recycling and reuse strategies help address the environmental and the economic challenges of water management in the Permian?
So Yeah, so we are definitely I think in Permian we are using quite a bit of produced water or water recycling. Uh, Also, as we say, like we are using quite a bit, we have to understand and accept that we produce a lot more water than what we are using. So definitely the amount and we still use quite a bit of water. So yes, using that recycled water is definitely putting less stress on the need of the fresh water and the environment and part of it. But it's not like it's a cure all part of it. We still have to worry about taking care of all the other remaining produced water, and how do we handle that. So definitely use of reduced water is helping us quite a bit, but it's still a small percentages. Yeah, so
One thing that was interesting that I found out, we use as much recycled, produced load fluid as we possibly can. And we've got the infrastructure working through third party companies to achieve that. But there are certain lease arrangements where we have to buy water from the farmer or the rancher out there. So you'll see these freshwater projects, or I use the word loosely, freshwater water that we buy from the rancher because that's in the terms that the landman had when we were doing our negotiation. That's the biggest driver in using fresh water today. Otherwise, we've got the infrastructure in most places, and we're really using that produced water. Then certainly that has a beneficial effect on the environment and reducing the amount we got to pump in a well, disposal well.
Thanks, Steve. And actually, we have about 3 minutes left. But since this question was about water management, I just would like to remind everyone that in about 15 minutes or so, there will be a panel entitled Sustainable Water Management in the Permian Basin. So we're going to talk specifically about that for those who would like to stay on and discuss it more. Um, so a lot more questions. I'm sorry if I'm gonna be missing obviously some, but the one of the question we had here, since we talked quite a bit about semi-frac and all of that, they are asking about how do you guys approach the subsurface metrics for semi-frac in general? Like, does this play a role in the choosing the semi-frac, or it doesn't really matter between heterogeneity between the different differences between wells?
so I can go quickly, and then Dave, maybe or Chin, you can add in there. So for us, when we talk about the subsurface design parameters, I'm talking specifically on the rate per cluster, because that's the rate per frac. That's the requirement that we have. After then, after that, to achieve the other operational efficiency, if we have to modify how many clusters per stage we are treating, what the rate we can achieve, how much equipment we need, what blender we need, those are manageable from the surface and the planning part of it. But from the subsurface, goal is to achieve the same rate per cluster, what we would have done in any frac job, whether it's simul, triple, or single zipper frac part of it.
Yeah, I mean that's one proviso that our people have abided by. We're doing the same rate per cluster. So if you're pumping 120 barrels per minute, which is often the case, now we're only in both wells. It's 60 barrels per minute per well. You're going to have to treat fewer clusters per stage. Again, the big metric is how much feet can you can you treat in a day. That's the one thing. That's the big cost driver, the big advantage of Simul-frack. A few other things though that may influence the design. Sometimes when we're pushing against each other, we're too close, and the fractures are migrating and converging, and we see adverse treating pressures. So then we'll stop and allow one well to go, say, 600-700 feet ahead, and then we'll resume the process. So that's an adjustment that's made on a well by well basis. and other things. Watching the things like the proppant concentration on either side, we found that one of our vendors had a setup where because you've got a clean side and a dirty side, and the two come together and go through a missile trailer, manifold system. And they were pumping 70% of their proppant into one side and 30% in another. And so, we got a real problem with that vendor that we're still working out. Other vendors, not a problem. And it's all the way that they set up their, thought ahead and set up their system. So, doing the quality checks there, because you can have weird stuff like that happening.
Thanks. We're actually out of time, but Qin, if you want to add something quickly, please do.
Just one thing for Oxy, when we're selecting the Simul-frack wells, we're trying to select the wells with the same landing, same completion design, same treating pressure. Yeah, for the wells that we treat together, that will help us achieve better uniformity. That's it.
Thanks, Qin. Thanks, Dave. Thanks, Amit. Ahmed, how do we get a copy of this recording? Because I was taking notes, but I wasn't fast enough to, capture this wealth of information that we got today.
I will send a copy to everybody. Don't worry.
All right. Thank you. I appreciate that. Thank you, everyone. Thanks, Dave. Thank you, everyone, for putting this together and for your time. Have a good day, everyone. Thank you.
Thanks, everyone. It was a pleasure.
Bye, guys.
Yeah.
Thanks. Bye-bye.
Bye.
Bye.